Good morning to one another. In the before session, we learn about the chemical kinetics. What is the chemical kinetics? And types of chemical reactions based on the velocity, rate of reaction, rate equation, rate constant and their units, and the significance of the rate constant, and how do we write the rate of reaction for different chemical reactions. Now we learn about the which factors are affecting the rate of chemical reaction. So now we learn about the factors are affecting the rate of chemical reaction. Rate of chemical reaction. So many factors are there to affect the speed of a chemical reaction. Rate means in the sense speed or velocity. So many factors are there to affect the rate of the chemical reaction. Example, first one is nature of the reactant. Nature of the reactants. Second one is total number of bonds. And third one is concentration of the reactant. Third one, surface area. Fifth one, light. Sixth one, temperature. It is very important. Temperature is very important. Based on the temperature, according to your examination purpose, give one problem from this temperature coming from this. And second, last one is catalyst. These are the factors to affect the speed of a chemical reaction. Now we are discussing one by one. First one, nature of the reactant. So how it is affected the rate of chemical reaction. We know in chemical bonding, majorly two types of bonds are there. Majorly ionic bond, covalent bond. So many bonds are there. Hydrogen bond, van der Waals forces are there. Metallic bond, coordinate covalent bond. But here we are taking in two bonds. That is ionic bond and covalent bond. The reaction between ionic substances. Much faster than the covalent substances. Reaction between ionic substances much faster than the covalent substances. That means if the reaction takes place in ionic substances as well as covalent substances, but which reaction is faster, how we can determine that one? Based on the bonds between the molecules, between the atoms. I give you one example, that is, if for example precipitation reaction you have to take it. Already we know one precipitation reaction, that is NaCl reacts with the AgNO3 to form NaNO3 plus AgCl. AgCl is the insoluble solid. Insoluble solid is called as what? Precipitate. Already I told you in the before class. Precipitate. Now Sima, NaCl is ionic compound. AgNO3 is also ionic compound. The reaction between the two ionic compounds is much faster than the covalent substances. I give one example for the covalent substances, that is ethyl alcohol. Ethyl C2H5OH. Ethyl alcohol reacts with the acetic acid, that is CH3COOH. What is the name for the CH3COOH? CH3COOH is common name is acetic ethyl alcohol. Now the reaction between ethyl alcohol and acetic acid, we are getting a product that is CH3COO C2H5 plus H2O. C2H5CH3COH is named as a ethyl acetate. Ethyl acetate. Now here two reactions are there, A and B. Now which reaction is faster? My question is which reaction is faster? How we can determine that one? Simple. A reaction is between the two ionic substances. B reaction is between two covalent substances. Ionic substances reaction is faster than the covalent substances because in ionic bond, in ionic compound, there is a no bond breaking and making between the two atoms. Attractive forces are presenting between the positive and negative ions. See my Na plus Cl minus. Between these two ions, there is a attractive forces are there. That's it. Here also same. Az plus NO3 minus. Attractive forces are between the two ions. So that's why here there is no bond breaking. But in a covalent compound, there is a need to break the bonds between the atoms. Carbon, hydrogen. There is a bond between the carbon and hydrogen. So that's why the time will be taken for breaking this bond to getting a product. So ionic compound substances more faster than the covalent substances. Reason is there is no bond breaking and bond making between the ionic substances. Already positive, negative, attractive forces are existing. Third, positive, negative, attractive forces, there is no need to break them. They are attract, this positive ion is attracted to the negative ion and negative ion attracted to the positive ion. There is no need to the break third specific attractions. But in the covalent molecules, what happened? There is a bond is existing between the two atoms. Carbon and hydrogen existing the bond. So that's why the bond breaking will be takes place. The time is required. So that's why the reaction is very slow compared with the ionic substances. Then second one is total number of bonds. Total number of bonds. Total number of bonds. See, I given one example, that is 2 moles of nitrogen monoxide react with the oxygen to form 2 moles of nitrogen dioxide. That is A reaction. And similar I given one more example. B, that is CH4 methane reacts with the oxygen, that is combustion reaction, to getting carbon dioxide plus water molecule. Now balance this equation. 4 hydrogens are there. So we take 2 in front of H2O and the reaction is balanced. Now which is the faster reaction? That can be explained by the total number of bonds between the reactants and products. See, nitrogen monoxide, the bond structure is N double bond O. 2 bonds are present between the nitrogen monoxide. How many moles are there? 2 moles. So that's why 2 into 2 bonds. Totally 4 bonds. Oxygen to oxygen molecule. 2 bonds are there. 2 plus 2, 2 into 2, 4 plus 2, 6. 6 bonds are there. Here NO2 molecule structure is N double bond oxygen and one coordinate covalent bond. Totally 3 bonds. 2 moles are there. 2 into 3. Why I taken the 3? Because 3 bonds are there. Why taken the 2 moles of NO2 is presenting. So totally how many bonds here? 6 bonds. So in NO reacts with the O2, we are getting the NO2, nitrogen monoxide reacts with the oxygen to get nitrogen dioxide. In this reaction totally 6 bonds breaking and 6 bonds formation will be takes place. 6 bonds breaking, 6 bonds formation is takes place. Keep in mind how many bonds? equal to the 6 bonds. Now another example, CH4. CH4, how many bonds are present between the hydrogen and the carbon? 4 bonds are there. 4 plus how many oxygens are there? Oxygen molecules, 1 oxygen molecule. Oxygen to oxygen, 2 bonds, double bond is there. So 2 oxygens, 4. So we require 2 moles of. So totally 2 moles of oxygen molecule is there. So 2 into 2. 4 plus 4. How many bonds here? 6 bonds. Then come to the CO2, carbon dioxide. Carbon between the oxygen, double bond is existing. Totally 4 bonds are presenting between the CO2 molecule and H2O. Oxygen is a central atom. Hydrogen. 2 bonds are there. 2 number of moles. So totally 2 into 2, 4. So that's why here 4 plus 4, 8. 4 plus 2 into 2, 4. That is 4 plus 4. That is 8 equal to the 8 mark. So in the A example, 6 bonds will be breaking and 6 bonds are forming. In the second example, 8 bonds are breaking, 8 bonds are forming. Less bond rearrangement reaction is faster than the more bond rearrangement. I will repeat once again. Lesser bond rearrangement reaction is faster than the more bond rearrangement reactions. Is it clear? So which reaction is faster than which one? A reaction is faster than the B reaction. Reason, less number of bonds rearrangement takes place in the A reaction compared with the B reaction. Then third one is concentration of the reactant. Third one is concentration of the reactant. Already we discussed this point in the previous section. Is it right or not? Are you remembering? That is rate of reaction directly proportional to the concentration of the reactant. I give one example to this also. Zinc granules. First of all, we take a test tube. To this test tube, we are taking the zinc granules. For that, we are adding HCl. First, we are adding the diluted HCl. After that, we are adding the concentrated HCl. So, what happened? While adding the HCl to the zinc granules, we are adding the zinc granule, HCl to the zinc granule. Zinc reacts with the concentrated HCl. We are getting zinc dichloride plus H2 gas. Releasing of the H2 gas is tested by we keep a burning matchstick to the mouth of the test tube. We get a pop sound. It indicates third reaction releases the H2. And second one is zinc is reacted with the diluted HCl. We are getting zinc dichloride plus H2 gas. But which reaction is faster now? How we can say which reaction is faster? Concentrated HCl or diluted HCl? Concentrated HCl reaction will give more amount of the H2 gas. Concentrated HCl will give more amount of the H2 gas. Why? What is the reason? Because concentration increases. See, it is a beaker now. It is a beaker. In this beaker, we are taking the concentrated HCl. Concentrated HCl means more number of HCl molecules are present in here. Is it right? Per unit value, the number of HCl molecules is more. HCl molecules is more. If the HCl molecules are more, the collisions are more. If the collisions are more, rate of reaction is also more. Keep in mind, rate of reaction majorly depends upon the collisions between the reactants. If the collisions are increases, effective collisions are increases, the reaction speed is increases. How we are know more. If the number of molecules are more, they are involving in collisions. Collisions like this. One molecule is collided with another molecule collided with another molecule, say another molecule. Like this, the collisions will be happen. So that's why the rate of reaction is also increases. Please keep in mind concentration of the reactant, that is the concentration of the reactant is increases, rate of reaction is also increases because the number of molecules per unit volume is more, they are involving in more collisions and so that's why rate of reaction is increases. Now we concluded that one thing, concentration of reactant directly proportional to the rate of a chemical reaction. Due to more number of molecules are involving in more effective collision, so that's why the rate of reaction is increases. Rate of reaction directly proportional to the concentration of the reactant. So here concentration of the reactant to the power of to the power of n. Rate is generally we are indicated minus d of x concentration by dt, that is directly proportional to the concentration to the power of n. Directly proportionality is removing by using a constant, you know that already, that is k. D of x concentration by dt, that is equal to the k into c to the power of n. So this is the concentration of the reactant. If suppose the reactants are present in a gaseous state, what happened? Rate is depends upon the pressure to the power of n. So minus of d of p by dt is directly proportional to the pressure of reactant to the power of n minus d of pressure, not here, constant, don't use the brackets because it is a pressure, p by dt, that is equal to the p to the power of p. No need to use the brackets now. When we are using the brackets, if that reactant is present in the aqueous state, if the reactant is present in the aqueous state, then only we are using the bracket. In the chemistry language, bracket indicates the concentration. So then p to the power of n, and directly proportional is removing by using a constant. These are three factors. Are you understood? First one is nature of the reactant, second one total number of the bonds, third one concentration of the reactant. Nature of the bond, ionic substances reactions faster than the covalent substances. Lesser bond rearrangement is faster than the more bond rearrangement. Concentration increases, rate of reaction increases because at the unit volume the number of moles are increases or the number of molecules are increases. They are involving in collisions. Collisions are increases, rate of reaction is also increases. Are you understood? Next one. Next one is surface area. Surface area. Surface area increases, rate of reaction is also increases. Example, surface area increases, rate of reaction increases. Directly proportional to the rate of reaction, because example for that, evaporation of water or evaporation of a tea in the saucer and in the cup, where the rate of reaction is more, where the evaporation is more, in a saucer compared with the cup. We are taking the tea in the cup and in the saucer now. Evaporation is faster in saucer because surface area is more, so evaporation is also more, but in the cup the surface area is less, so the evaporation is also less. So finally surface area increases, rate of the reaction is also increases. Are you understood? I will repeat once again. We are taking the cup, we are taking the tea in the cup and also in the saucer. Where the evaporation is more? In the saucer. In the saucer, the tea evaporation is more. It will be cooled very fast because surface area is more. So that's why evaporation is also more. But in the cup, surface area is less compared with the saucer. So evaporation is also less. So rate of evaporation is directly proportional to the surface area. That is, rate of reaction is directly proportional to the surface area. Like example, some reactions takes place in the presence of light only. They are not carried out in the presence of dark. Some reactions does not takes place at a dark conditions. They require the light. Third type of reactions are called as a photochemical reactions. So if the light is there, the rate of reaction is also more. I will repeat once again. Some reactions are affected by the light. Some reactions takes place in the dark conditions. If some reactions does not takes place in the dark conditions, for that reactions are required the light. Third type of reactions are called as a photochemical reactions. So photochemical reactions, light increases, rate of reaction is also increases. Photochemical reactions. Photochemical, here in the name also you observe. Photo means light, chemical means chemistry, that is the reactants are converted into the products. So in the presence of light, that is H nu, is increases, rate of reaction is also increases. Then next, the important one is temperature. It is very, very important. Temperature. Now we discussing about how the temperature affect the rate of reaction. Temperature. Temperature increases, rate of reaction increases. So, rate directly proportional to the temperature. Rate directly proportional to the temperature. For most of the cases, if we are increased 10 degree centigrade or 10 Kelvin temperature, the rate constant, that is K value, will get double. For most of the reactions, we are increasing the 10 degree centigrade or 10 Kelvin temperature, the rate constant K value will get double. Now that I am explaining, taking an example, H2 reacts with the I2 to get 2HL. H2 molecule, that is H and H, iodine. Now this also represented like this. This is also represented. See, hydrogen plus iodine to get bond breaking takes place between hydrogen, iodine. At the same time, bond formation takes place between the hydrogen and iodine. Bond breaking between the hydrogen, iodine. At the same time, bond formation will be takes place between the hydrogen and iodine. That is represented like this: hydrogen, iodine, bond breaking. So that's why they are indicated the dotted lines. Bond breaking between the iodine indicated by the dotted lines. Bond formation is also takes place. After that, we are getting a product, that is hydrogen iodine plus hydrogen iodide. So this is called as intermediate state. Or activated complex, activated complex or transition state or transition state. Intermediate state, activated state or transition state. Now that same reaction, now I explain by taking a graph, that is similar. On the here now I am taking a graph. On the y-axis, potential energy. On the x-axis, reaction coordinate we have to take it. Reaction coordinate. What is the meaning of reaction coordinate? You know? Reaction coordinate is the profile. Reaction coordinate represents the profile of energy change. It indicates energy change when the reactants are converted into the products. Reactants are converted into the products now. In that purpose, how the energy changes takes place, that can be explained, that can be represented by the reaction coordinate. Now here, these are reactants are converted into the products. It is one of the graph now. Reactants are converted into the products after passing the energy barrier. It is called as energy barrier. For all reactions, reactants are converted into products after passing the energy barrier. So it is a potential energy. For example, 10 calories, 20 calories, 30 calories, 40 calories, 50 calories, 60 calories, 70 calories, etc. Now reactants are having some amount of energy. The minimum amount of energy containing by the reactants is called as a average kinetic energy. The minimum amount of energy containing by the reactants is called as a average kinetic energy. There is not a sufficient energy. Kinetic energy is not a sufficient energy to convert into the products. So it is reactants energy. The reactants energy is not sufficient to convert the products. If the reactants are after passing the energy barrier, then only it is converted into the products. Reactants are after passing the energy barrier, then only they are converted into the products. So here this is the reactants energy. And it is energy B. After passing the energy barrier only they are converted into the products now. That means it requires some additional amount of energy. This is some additional amount of energy. Reactants energy is energy barrier of third reaction is here. Energy barrier is 70. Assuming reactants energy 30. The reactants are converted into the products after passing the energy barrier. That means it required 40 amount of energy. Extra amount of energy is needed. That extra amount of energy is called as a activation energy. What is activation energy? Reactants are converted into the products after passing the energy barrier. Reactants are having some minimum amount of energy. Reactants are having some minimum amount of energy. That energy is called as a average kinetic energy. That average kinetic energy is not sufficient to convert it into the products. It requires some amount of external energy for the conversion to the product. That external energy is called as a activation energy. From here to energy barrier, from here to energy barrier, the total amount of energy is known as threshold energy. Threshold energy. So threshold energy is equal to threshold. What is the threshold energy? Total energy. That is average kinetic energy plus activation energy. Threshold energy is equal to average kinetic energy plus activation energy. From this equation, I want activation energy. So average kinetic energy come to the LH side. So that is threshold energy energy minus average kinetic energy is equal to activation energy. So how we define the activation energy? For 2 marks it is very very important. What is activation energy? The difference between threshold energy and average kinetic energy is called as a activation energy. What is the activation energy? How it is defined? Difference between threshold energy and average kinetic energy. So what you understood based on this one? Reactants converted into the products after passing the energy barrier. This is for this. But we are here discussing about the temperature now. How the temperature affected, next we have to discuss it. Before going to that, for example, we are taking a sample in a cubic. For example, we are taking a sample in a cubic. This is a cubic. Here we are taking a sample. This is containing different types of molecules. For individual molecules, kinetic energy does not calculated accurately. It is not possible to calculate accurate kinetic energy for individual molecule. Individual molecule kinetic energy does not measure accurately. So that's why we have to take in the group of molecules, more number of molecules or large number of molecules. Large number of molecules kinetic energy can be calculated. So that's why we take in a graph that is. So this is the graph now. On the y-axis we are taking the fraction of molecules, that is Ne by Nt. Ne by Nt is called as a fraction of molecules versus potential energy or reaction coordinate. Potential energy or kinetic energy. Here we are taking the potential energy or kinetic energy to kinetic. Taking the kinetic energy. On the y-axis, fraction of molecules. On the x-axis, kinetic energy. We are getting a graph like this. Yeah. Number of molecules, for example, 10 molecules, 20 molecules, 30 molecules, 40 molecules, 50 molecules here, 50 molecules. Most of the molecules are having the same kinetic energy, so that's why it is called as a most probable velocity. Most probable velocity. Are you understood? What I am saying here? See here, 10 molecules, 20 molecules, 30 molecules, 40 molecules, 50 molecules. 50 molecules are having the same energy. That is called as a most probable velocity. How we can define most probable velocity? Most of the molecules are having the same kinetic energy. Most of the molecules are having the same kinetic energy. That energy is called as a most probable velocity. Now, at T temperature, it is at T temperature. I will draw one more graph. See here. At T temperature, Ne by Nt, that is fraction of molecules versus kinetic energy. At T temperature, these molecules are involved in a reaction. So this area shows number of molecules reacted, fraction of number of molecules reacted at T time. In the T time, these number of molecules are involving in reaction, that is sigma. A, B, C, D. These area of the molecules are involving in the reaction. If we are increasing the temperature, see, if we are increasing the temperature, reactions are participating in the chemical reaction, that is nearly double to these area. Nearly double to these area. These are named as E and F. So if we are increasing the temperature, this graph at T plus 10 degrees centigrade. If we are increasing the 10 degrees or 10 kelvins temperature, the number of molecules involved in the rate of reaction is more compared with that T temperature. These can be this area shows the number of the fraction of molecules, additional molecules reacted at T plus 10 degree centigrade. So the number of at T temperature, the number of molecules, these are the number of molecules. If we are increasing the 10 degree centigrade, the fraction of molecules are involved in the rate of reaction is more. So that is represented by using a temperature coefficient. Temperature coefficient. Temperature coefficient. Temperature coefficient, that is equal to the, how do we define the temperature coefficient? How do we define the temperature coefficient? That is sigma. The ratio between specific rate constant at different temperature. That is K is the specific rate constant at T temperature, specific rate constant at T plus 10 degree centigrade. The ratio between the specific rate constants with the different temperature, the different temperature differed by the 10 degree centigrade. Here generally temperature is 25 degree centigrade. If T plus 10 degree centigrade is 35 degree centigrade. So I will repeat once again the definition for the temperature coefficient. Ratio between specific rate constant K, specific rate constant measured at different temperatures, that is called as a temperature coefficient. Nearly temperature coefficient for a chemical reaction is equal to the 2. For some more reactions, the K value may be 3. Example for this is H2 react with the half moles of O2, we are getting H2O. At room temperature, it is very slow. At room temperature, the reaction rate is very slow. But the same reaction takes place at a high temperature. The same reaction takes place at a high temperature. The rate of reaction is very fast. This is the example for the rest. So, I understood? Temperature increases, rate of reaction is also increases. For that purpose, we are taking a temperature coefficient. For most of the reactions, we are increasing the 10 degree centigrade or 10 Kelvin temperature. The specific rate constant will get double. Or some more reactions, it is a triple. Make it more. Then next, in the temperature, Arrhenius give the relationship, quantitative relationship. Arrhenius scientists to given the quantitative relationship between the temperature, rate constant, Arrhenius equation. Arrhenius scientists to given the quantitative relationship between rate of reaction, temperature and rate constant. It gives the relationship between the temperature, rate of reaction and rate constant. Arrhenius equation is K is equal to A to the power of minus EA by RT. It is Arrhenius equation. This is Arrhenius equation where K is equal to rate constant, A is exponential factor or frequency factor. Frequency factor. Keep these three names. It is important. And then keep in mind. EA is activation energy. Activation energy. And then R is gas constant. T is temperature in Kelvin. Temperature in Kelvin. Now we take the log both sides, natural log. So that is ln K is equal to power is E minus EA by RT is present in the power. It will come to the base, that is minus EA by RT plus ln A. The same reaction is taken in another way, that is ln K is equal to minus EA by R 1 by T plus ln A. For our convenience, I can write the equation rearranged in that way. Y, this is taken as a y is equal to mx plus c. Now I can draw a graph for that equation. We are getting like this. Y on the y axis ln K, on the x axis 1 by t. Now the slope is minus EA by R. This is the slope, negative slope, and the intercept is ln A. And at T1 temperature, the same equation at T1 temperature we can write. At T1 temperature, the same equation is written in the form of ln K1 is equal to minus EA by R T1 plus ln A. For at a different temperature, at T2 temperature, the equation is written ln K2 is equal to minus EA by R T2 plus ln A. ln A are both are constant, so there is no need to take in that. And this is the equation 1 and equation 2. Now subtract equation 2, equation 1. We are getting ln K2 minus ln K1 is equal to minus EA by R T2 minus of minus EA by R T1. Minus of minus, it taken minus of minus plus, so minus EA by R T2 plus EA by R T1. Now this is rearranged like this, that is EA by R T1 minus EA by R T2. Here ln K2 minus A, that is log A minus log B. Log A minus log B is a log A by B. So ln K2 by K1. Here EA and R is common, so for taking it common, ln K2 by K1 is equal to EA by R 1 by T1 minus 1 by T2. It is present in the natural log. Suppose it is converted into the log base 10, that is log K2 by K1 is equal to the EA by 2.303 into R 1 by T1 minus 1 by T2. So this is the Arrhenius. Arrhenius is also express the temperature effect on the rate of reaction by quantitatively. We take the physical quantitatives to explain that. So by taking the different temperature, definitely the K value is also different. So by getting that, we can predict the rate of reaction. And the last one is catalyst. So what is the catalyst? That is a substance to increasing the or decreasing the rate of reaction. Catalyst is a chemical substance. Catalyst is a chemical substance next one. Catalyst is a chemical substance which alerts the rate of chemical reaction. Which alerts the rate of chemical reaction. It is two types. Positive catalyst and negative catalyst. Positive catalyst and negative catalyst. Positive catalyst, how it affects you. How the affects positive catalyst. It is a reaction coordinate. Reaction coordinate, and it is a potential energy. Potential energy. Now the reactants are converted into the products. Reactants are converted into the products. If we are using the positive catalyst, see, it is the activation energy. This is the activation energy, EA. If we are using the positive catalyst, what happened? The activation energy. The activation energy. The activation energy. The activation energy is decreases. The rate of reaction is increases. This is the activation energy. So which activation energy is more now? EA1. It is EA1. So this is the path of reaction. Path of reaction. In the presence of catalyst. In the presence of catalyst. It is path of reaction without catalyst. Activation energy by using a catalyst like this. Activation energy without the catalyst. So here EA and EA1, which is more? Here EA1. EA is more. If the activation energy is more, rate of reaction is less. Activation energy is more, rate of reaction is less. That is inversely proportional. Activation energy and rate of reaction both are inversely proportional. By using a positive catalyst, activation energy is decreases, rate of reaction is increases. Activation energy decreases, rate of reaction is increases. Negative catalyst. What happened in negative catalyst? See, rate of reaction like this. Reactants are converted into the products. We are using the positive catalyst. We are using, this is the activation energy, EA. We are using positive, negative catalyst, the activation energy C. Which is more? Which is more now? EA1. Here which is more? EA1 is more. EA1 is more than the EA. If activation energy is more, rate of reaction is slow. Finally, I have concluded one thing, that is, catalyst is a chemical substance which alerts the rate of reaction. If we are using the positive catalyst, activation energy decreases, rate of reaction is increases. If we are using the negative catalyst, activation energy increases. Activation energy increases, rate of reaction is decreases. Activation energy is decreases when you are using the positive catalyst. Activation energy is increases when we are using the negative catalyst. Activation energy is less, rate of reaction is more. Activation energy is more, rate of reaction is less. That's it. Thank you. Then next our topic is order of reaction. Next our topic is, before entering to the order of reaction, based on the number of steps, reactions are classified into two types. Based on the number of steps, reactions are classified into two types. Based on the number of steps, reactions reactions are classified into two types. They are elementary reactions and complex reactions. Elementary reactions and complex reactions. Elementary reactions means the reactions which are completed in a single step. They are called as elementary reactions. The reactions which are completed in a single step, they are called as elementary reactions. Example: iodine hydrogen reaction gives rise to form the hydrogen iodide. Nitrogen oxygen molecules react with each other to form nitrogen monoxide. Ammonium, that is NH4, nitrate, NO2, ammonium nitrate on decomposition, ammonium nitrate on decomposition it releases N2 and H2O, water molecule. So these all reactions are takes place in a single step. So that's why they are called as elementary reactions. Second one is complex reactions. Complex reactions. The reactions which are completed two or more elementary reactions. The reactions which are completed more than the one step. They are called as complex reactions. More than the one step. Third type of reactions are called as complex reactions. Example: conversion of a ozone to oxygen molecule. Decomposition of a ozone molecule to oxygen. 2 number of moles of ozone on decomposition it gives 3 moles of oxygen, and decomposition of hydrogen peroxide. In the presence of iodine and in the presence of basic medium is also example for the complex reaction. Two moles for balancing the equation. So based on these steps, reactions are classified into two types: elementary reactions and complex reactions. Elementary reactions which are completed within single step. Complex reactions are completed more than the one step. They are called as complex reactions. Order of a reaction. Next our topic is order of a reaction. Order of a reaction. So what is order of a reaction? The sum of power of concentrations of reactants. Sum of power of concentration of reactants in the rate equation or in the rate law, they are called as a order of reaction. So how we can define the order of a reaction? Sum of power of concentration of reactants in rate equation. Keep in mind, it is very important. In rate equation, that is called as a order of a reaction. For example, I given one example, that is A moles of A reacts with the B moles of B to form the products. For this type of reaction, we can write the rate. Rate is equal to K into A concentration to the power of the small a, B concentration to the power of small b. So what I am saying, sum of power is A and another power is B. The total sum A plus B is called as a order of a reaction. So A plus B here called as a total order of a reaction. And small a is a order with respect to the A. Small b is also order, but with respect to the B. Individual orders for A is small a, individual order for B is small b. Total order of the reaction is A plus B. And reaction may be 0, positive or negative or fractional value. It is calculated experimentally. It is calculated experimentally but not theoretically, and it does not depend upon the stoichiometric coefficients in the balanced equation. Keep in mind, it is very very important, and it is does not depend upon the order of a reaction. Does not depends upon the number of stoichiometric coefficients. Does not depend upon the stoichiometric coefficients in the balanced chemical equation, and order of a reaction is applicable for elementary reactions as well as complex reactions. Order of a reaction is applicable for elementary reactions as well as complex reaction. I give some examples how to determine the order of reaction. For example, I am taking the A gives rise to the products. This is one example. So how we can write the rate for this equation, this reaction? Rate is equal to K into A to the power of, here nothing is there means 1, but here it is a 0 order reaction. The power should be 0. The power should be 0. If the power is 0, sum of powers what happens? 0. So it is a which type of reaction? It is a 0 order reaction. 0 order reaction. Order of reaction units are depends upon the rate constant. Note that point. Order of reaction units. Order of reaction units are depends upon rate constant, that is K. Order of reaction units are depends upon the rate constant. What is the rate constant units, ma'am? Rate constant K is equal to mole to the power of 1 minus n into liter to the power of n minus 1 into second inverse. So this is the order units for the rate constant. Here n value is 0. In 0 order reaction, n value is equal to 0. In place of n, we have to take the 0 for the calculating of the units of a rate constant. So K is equal to mole to the power of 1 minus 0 into liter to the power of 0 minus 1 into second inverse. So what happened after solving this one? Mole to the power of 1, liter to the power of minus 1, and second inverse is the units for the rate constant, and also units for the 0 order reaction. Units of the 0 order reaction. Order of reaction units depends upon the rate constant. And second one I am taking the first order reaction, that is A, same one. A gives rise to the products. So how we can write the rate? Rate is equal to K into A to the power of 1. Why madam you are taking here 0 and here taking 1? Because here the concentration of the rate does not depend upon the concentration of the reactant in 0 order reaction. Rate, that means speed, does not depend upon the concentration of the reactant. So that's why here power should be taken as a 0. But in the first order reaction, rate is depends upon the concentration of the reactant. Rate is depends upon the concentration of the reactant. So here n value is taken as 1. By taking the n, what is the units for the 0 order reaction? K is equal to mole to the power of 1 minus 1 into liter to the power of 1 minus 1 into second inverse. So after solving 1 minus 1 0, 1 minus 1 0. Mole to the power of 0, it is 0. So mole 0, liter 0. Finally we are getting second inverse. So what is the units for the 0 order reaction? Sorry, first order reaction is second inverse. It is example for the first order reaction. Then second order reaction take. We have to take the third one. Second order reaction, that is 2A moles of A reacts with itself to form the products. For this, how we can write the rate? Rate is equal to K into A to the power of 2. What is the power, ma'am? 2. Sum of power of concentration. What is the sum here? 2. So order of order reaction. Second order reaction. How we can write the units? K is equal to, what is the n value here? N value is 2. In place of n we have to take any 2. So 1 minus 2 mole to the power of 1 minus 2 into liter to the power of 2 minus 1 into second inverse. So K is equal to mole to the power of minus 1 into liter to the power of 1 into second inverse is the units for the second order reaction. Third order reaction. Next example is third order, that is 2 moles of A react with 1 mole of B to form the products. For this, how we can write the rate? Rate is equal to K into A to the power of 2 into B to the power of 1. What is the sum here? 2 plus 1 is equal to 3. So what is the order of a reaction? 3. Sum of power of concentration of reactants is known as a order of reaction. So N we have to take in the 3. What is the unit for the third order reaction? Mole to the power of 1 minus 3 into liter to the power of 3 minus 1 into second inverse. After solving this one, we are getting mole to the power of minus 2 into liter to the power of 2 into second inverse. That is units for the third order reaction. In your examinations, they given the rate constant units. Rate constant units. By seeing the rate constant values also we can say that is which type of a reaction. For example, ethyl acetate is involves in a hydrolysis. We are getting the acetic acid and alcohol. Ethyl acetate is involves in hydrolysis. We are getting the alcohol and acetic acid. For that reaction, K value is, for that reaction, K units, not K value, K units, K value. Okay, K value 2 into 10 to the power of minus 8 second inverse, and asking that is which type of a reaction, which order of a reaction. By seeing the unit, second inverse. Second inverse is the unit of which order? First order. So it is which type of reaction? First order reaction. By seeing the units also we can say the type of a order of a reaction. Once again I repeated based on the number of steps, reactions are classified into two types: elementary reactions, complex reactions. Elementary reactions are completed in a single step, complex reactions are completed in a multi steps. And order of a reaction is sum of power of concentration terms in a wave equation is known as a order of a reaction. Order of a reaction values are maybe 0, positive or in fractional. It is experimental. It is not a theoretical. By seeing the equation, we cannot say the order of a reaction. Now later on I explain that one. The next one, rate of reaction does not depend upon the stoichiometric coefficients in the equation, and it is applicable for elementary reactions and complex reactions. Then I given an example how we can see this order of reactions. See I given an example here. N2 plus O2 reacts with each other to form 2NO. Or another example. For this, how we can write the rate of a reaction? Rate is equal to K into N2 plus O2. N2 power is 1, O2 power is also 1. So what is the sum of power of concentration? 1 plus 1, that is 1 plus 1 is equal to 2. So it is a which type of reaction? Second order reaction. How we can say? By seeing the number of coefficients in the balanced chemical equation. What is the coefficient here? 1. What is the coefficient of the oxygen? 1. By sum the two coefficients we are getting 2. So it is example for the second order reaction. Assuming. How we can say? By seeing the stoichiometric coefficients. But it is not a theoretical one. It is a experimental one. For that I given one example, that is conversion of a O3 molecule to oxygen. How we can write the rate equation? Rate is equal to K into O to the power of 2. So what is the order of a reaction for this one? The power of sum of power of concentration is 2. It is a second order reaction. How we can say it is a second order reaction? By seeing the number of coefficient in the stoichiometric balanced equation. Is it right or wrong? But it is not a second order reaction. It is not a second order reaction because it is a complex reaction. O3 is converted into O2. O3 is converted into the O2. It is a which example? Complex reaction. N2 is N2 O2 reacts with each other to form the NO. It is example for the elementary reactions. For elementary reactions, keep in mind, for elementary reactions, the order is always equal to the power of coefficients, sum of power of coefficients that can be seen by the balanced chemical equation. But for the complex reactions takes place in a multi-step. First step, in the first step, ozone is converted into the O2 plus oxygen. It is a reversible reaction and it is a very fast reaction. Second step, in the second step, nascent oxygen, single oxygen is called as a nascent oxygen. Nascent oxygen reacts with the ozone to get oxygen molecule. It is slow step. Slow step is called as a rate determining step. Slow step is called as a rate determining step. Rate determining step or rate limiting step. Because this reaction can fix the order of a reaction. It is controlled the overall reaction. Overall reaction is controlled by the slow step. So that's why that is called as a rate determining step or rate limiting step. Now we can write the rate equation for this slow step because it is only determining the rate now. So that's why for this reaction only we can write the rate. So rate is equal to K into O3 concentration into O concentration. See ma, rate for which type of reactions we can write rate? Rate is equal to K into concentration of the reactants. But here concentration O3 is there, here also O3 is there. But nascent oxygen is there now in the balanced equation? No. So for finding the nascent oxygen concentration, we have to take in the fast reaction. Fast reaction is a reversible reaction. For reversible reaction, we have to take in the equilibrium constant, that is Kc. How we can write the equilibrium constant? We learn already. This is in the first year now. Equilibrium constant Kc is equal to product of product concentration by reactant concentration. Product of product concentration by product of reactant concentration. In fast reaction, O2 and oxygen is the product, O3 is the reactant. So O2 concentration into O concentration by O3 concentration. From this equation we are getting the oxygen. We want oxygen concentration. So O concentration, O2 and O3 is come to the LH side. So getting Kc into O3 concentration by O2 concentration. This total term when it will come to the LH side, it will be reversed. Now in the place of O concentration in the first equation, we substituted the equation 3. So rate is equal to K into O3 concentration into Kc concentration into O3 by O2 concentration. K is constant, Kc is also constant. Constant into constant. One more constant, that is R is equal to K dash O3 concentration into O3 concentration by O2 concentration. O3 into O3, K dash O3 into O3, that is O3 square. O2 is present in the denominator, it will come to the numerator. be 2. 2 plus minus 1. 2 plus minus 1 is, that is 1. So what is the order of this reaction? Order of this reaction is first order. Order of reaction is first. By seeing the balanced chemical equation, we are getting how much of order? Second order. But it is experimental. Experimentally, we have to find out the order of reaction is 1. That is the difference. You understood? Order of a reaction does not depend upon the stoichiometric coefficients in the balanced chemical equation. Order of a reaction is can be calculated by the experimentally. It is not a theoretical one. And one more thing here. The total order of a reaction is 1. What is the order of reaction for the O3? Order of reaction for O3 is 2. Order of reaction for O2 is minus 1. Order of a reaction with respect to the O3 is 2. Order of a reaction with respect to the O2 is minus 1. And then next one, molecularity. So what is the molecularity? Molecularity. Molecularity means the number of molecules which are present in the elementary step. The number of molecules which are present in the elementary step of a reaction is known as a molecularity. Elementary step. In complex reactions, see one example. This is the example for the complex reaction. Isn't it or? But it takes place in 2 steps. One elementary step, another elementary step. In the elementary step, which one is the slow reaction? This is the slow reaction. In the slow reaction, how many molecules are present in? 2 molecules are present. Now for this reaction, molecularity is 2. Molecularity is 2, but order is 1. Keep in mind. Complex reactions, molecularity is not equal to the order of reaction. For elementary reactions, order is equal to the molecularity. So what is the molecularity? Molecularity is a number of molecules which are present in a elementary step of a chemical reaction is known as a molecularity. Molecularity value either 0 or positive, but not negative and fractional. But not negative and fractional. It may be 0 or positive. Molecularity does not exceed 3. The maximum molecularity of a chemical reaction is 3, and it is a theoretical one. Molecularity is a theoretical one, and it is applicable for only elementary reactions but not to the complex reaction. That is the difference. According to your intermediate examination purpose, the difference between the order of reaction and molecularity is generally asking a question. So you can write based on the explanation. The next one is zero order reaction integrated equation. Zero order reaction integrated. One more. Pseudo order reaction. Pseudo unimolecular 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 reaction means order of reaction is 1. Order is 1, but molecularity is 2. Molecularity is 2. Example, hydrolysis, esterification. Esterification in the presence of acid. Esterification in the presence of acid. Example, CH3 COO C2H5 plus H2 gives rise to the CH3CF. This bond will be break down and add to H2O na 2 hydrogens 1 oxygen. OH is added to this side, H is added to this side, that is hydrolysis. CH3 COOH plus C2H5OH we are getting. This is called as a hydrolysis of a ester in the presence of acid. Hydrolysis of a ester is also known as a esterification. For this we can write the rate. Rate is equal to K into CH3 COO C2H5. Ester, it is a ester. Ester concentration into H2O concentration. But H2O concentration you have to take in the excess quantity. H2O taken in a excess quantity, so that's why H2O does not affect the order. H2O does not affect the order because it will taken in a excess quantity. So order of the reaction for this reaction is 2. But how many molecules are participating here? 2 molecules are participating, so it is a bimolecular. Order of reaction is 1, but molecularity is 2. So it is example for the pseudo unimolecular reactions. And one more example is there. Inversion of a cane sugar. Inversion of a cane sugar. Already I told you that is C12 H22 O11 plus H2O gives rise to the C6 H12 O6 plus C6 H12 O6. One is glucose, another one is fructose. Now for this rate is equal to the K into C12 H22 O11 into H2O concentration. Here also same. Water is taken in a excess quantity, so that's why it does not affect the order of a reaction. But how many molecules are participating here? 2 molecules. Order is 1. H2O to the power of 0. It does not affect the order of reaction. But molecularity is 2. That type of reactions are called as a pseudo unimolecular reactions or pseudo first order reactions. The next one is integrated equation for zero order reaction. Zero order reaction. So A gives rise to the products. For writing the rate is equal to K naught into A to the concentration of 0. Because it is a zero order, how we can define the zero order? The rate of a reaction does not depend upon the concentration of the reactant. So that's why we have to take in here power 0. Rate of reaction does not depend upon the concentration of the reactant. So that's why we have to take in the 0. How we can write the rate? Minus D of A concentration by dt concentration is equal to K naught into A to the power of 0. Anything power 0 will be 0. So that's why next one is minus dA by dt is equal to K naught. dt is come to the RH side. We are getting minus D of A concentration is equal to K naught into dt. Integrated both sides. We are getting integrated both sides by taking the limits A into A minus x. Minus here, and D of A concentration is equal to K naught into time limit 0 to t, that is dt. A is initial concentration of the reactant. Concentration at time is equal to 0. Product concentration 0. At T1 time, some amount of A is decreases. How much of amount of A is decreases? Minus X amount of A is decreases. How much of product is formed? Plus X amount of a product is formed. Initial concentration. Totally how much of A is presenting after T time? Totally, how much of A is present in after T time? That is A minus X. So, A is the initial concentration of the reactant. A minus X is the concentration of the reactant after the T time. Now, after applying the integration on both sides, differentiation and integration both are cancelled because these two are opposite sides. So, we are getting minus of A concentration into A minus X, that is here K naught into T to the 0 to T limits. After applying the limits, upper limit minus lower limit, that is A minus X minus A K naught into upper limit T minus 0, upper limit minus lower limit. Minus will enter into the brackets. We are getting minus of minus AX plus A is equal to K naught T minus 0 T. So by rearrangement this equation, we are getting K naught into T is equal to A minus X. We want K naught, so that's why K naught is equal to A minus X by T. After minus is entered into this is one of the equation, and one more simple form is if minus enters into the brackets, we are getting K naught A minus A plus X by T. Plus A minus A both are gets cancelled, so finally we are getting K naught into X by T. This is one of the integrated equation for this zero order reaction. And one more, half-life. See, A reactants are converted into the products. Initial concentration initial concentration A and initial concentration is 0. Time is also 0. If time is 50%, that is half. If time is equal to half, initial concentration is decreased by the half of the initial concentration is decreased. Half of the initial concentration will be formed. That is X also is equal to the A by 2. That is, what is the T of? Half-life. Half-life is indicated by the T of. What is the meaning of T of? The time is required. Time is required to consume half of the initial concentration of the reactant is known as a half-life. Time is required to consume half of the initial concentration of the reactant is called as a half-life. For taking here, in the place of X, we have to take in the A by 2. In the place of T, we have to take in the T of. So that K naught is equal to A by 2 T of. We want T of, so T of is equal to A by 2 K naught. By using this, we are calculating the half-life for the zero order reaction. By same method, we are applying for the first order reaction also now. First order reaction. For first order reaction, the integrated equation is K is equal to 1 by 3 ln A by A minus H. If ln is come to the log base 10, K1 is equal to 2.303 by 3 log A by A minus H. This is integrated equation for the first order reaction. T of is equal to 0.693 by K1 for half-life for the first order reaction. Thank you.
Welcome back, dear students. It has been a while. We have started this topic, Demoivre's theorem. Actually, this topic should be discussed after completion of the first topic, complex numbers. So, maybe it has been difficult for you to understand what's Demoivre's theorem, what is a mode amplitude form, what are the eighth roots of unity, etc. etc. Now since you have completed the first topic, you have studied the first topic complex numbers in total. Now we are ready to discuss De Moivre's theorem and its applications and a few problems, and important problems. Yes. Right. So let's start with the mode amplitude form. We know that any complex number z, which is a plus ib, can be converted to the mode amplitude form, which in fact is modulus amplitude form, which is r into cos theta plus I sin theta. And in the short form, we write this cos theta plus I sin theta as r cis theta. We call this, or we write this, r into cos theta plus I sin theta, which is actually r cos theta plus I into r sin theta. That r into cos theta plus I sin theta. In short form, we will write it as r into cis theta. So any complex number z, which is a plus ib, can be converted to this structure r into cos theta plus I sin theta, where r is square root of a square plus b square, which is exactly modulus of this complex number z. R is the modulus of the complex number z. And this theta, which is tan inverse b by a. Theta is tan inverse b by a, which is called the amplitude, of the complex number z. That's why this structure r into cos theta plus I sin theta should be called the modulus amplitude form of the complex number z. So what is the importance of this modulus amplitude form? Its importance is it allows us to find product of complex numbers much more simply. It allows us to find the powers of complex numbers much more simply. It allows us to find the quotient of two complex numbers much more simply. And it allows us to find the roots of the complex numbers in a convenient and simple form. Okay. So for that, we are going to use a specific theorem which is called De Moivre's theorem. Of course, that's the name of the mathematician who has proposed the theorem and proved that. So this De Moivre's theorem. What is this De Moivre's theorem? This De Moivre's theorem states that any complex number cos theta plus I sin theta when it is raised to a power n, that is cos theta plus I sin theta to the power of n, it's nothing but cos n theta plus I sin n theta for all n belongs to z plus, and for all n belongs to z minus, in particularly for 0 also. So we are going to write this one as for all n belongs to z, which is set of integers. Since we are already using the symbol z for complex numbers, we are not going to use the symbol z for the set of integers. So we are going to denote the set of integers with the symbol I. So cos theta plus I sin theta to the power of n is cos n theta plus I sin n theta for all n belongs to I, which is the set of integers. Which is the set of integers. So in simple, if you have a complex number of the form cos pi by 3 plus I sin pi by 3, if this is our z, which is cos pi by 3 plus I sin pi by 3, then what is z to the power of 8? The answer is simple. Cos pi by 3 plus I sin pi by 3 whole to the power of 8. And this is nothing but cos 8 pi by 3 plus I sin 8 pi by 3. That is so simple. If it is z to the power of 12, so what should be the answer? The answer is simple. Cos pi by 3 plus I sin pi by 3, which is our z to the power of 12. So by virtue of this De Moivre's theorem, cos theta plus I sin theta whole to the power of n is cos n theta, which is cos 12 into theta, which is pi by 3, plus I sin 12 into pi by 3. So on simplification, this becomes cos 4 pi plus I sin 4 pi. By the way, what is this cos 4 pi? Cos 4 pi is nothing but cos 0. Sin 4 pi is nothing but sin 0. So what is this cos 4 pi plus I sin 4 pi? The answer is cos 0 plus I sin 0, which is, so z to the power of 12 is cos 4 pi plus I sin 4 pi, which is exactly equal to cos 0 plus I sin 0. And cos 0 is 1 and sin 0 is 0, so the answer is 1. That's it. So it's as simple as that. Straight away you can write z to the power of 12 using De Moivre's theorem, this one cos 4 pi plus I sin 4 pi. On reducing this n pi or n theta, which is this 12 into pi by 3, which is this 4 pi, into the interval, primary interval 0 to pi by 2, you can reduce any angle to the interval 0 to pi by 2 using the trigonometric formula you have. Cos 90 plus theta is sin theta. Cos 180 plus theta is minus cos theta. Cos 270 plus theta is 270 is 3 into 9 by 2. So cos converts to automatically sin. 3 pi by 2 plus theta is in the fourth quadrant. In the fourth quadrant, cosine is positive. So cos 3 pi by 2 plus theta is sin theta, etc., etc. So with those formula you can use to reduce this n theta to the primary interval. You can reduce this n theta to the primary interval 0 to pi by 2. Once you reduce this to this interval, you can easily write what is this cos n theta, what is this sin theta, and you can replace those values, and you are going to get cos theta plus I sin theta to the power of n. So this De Moivre's theorem allows us to find the powers of complex numbers straight away in just 2 steps. Okay, so before that, let's see what are some important properties of this modulus amplitude form. So if Z1 is a complex number, or 1 into cos theta 1 plus I sin theta 1, or 1 into cos theta 1 plus I sin theta 1. That is our Z1. And Z2 is another complex number, which is R2 into cos theta 2 plus I sin theta 2. Z3 is another complex number, whose modulus is R3, amplitude is theta 3. So it is R3 into cos theta 3 plus I sin theta 2. By the way, what are the short forms for this? The short form for Z1 is R1 into sec theta 1. The short form for R2 into cos theta 2 plus I sin theta 2 is R2 into sec theta 2. And this is R3 into sec theta 3. So these are the short forms for it. Now, what is this Z1 into Z2? The product of the two complex numbers, which is R1 cis theta 1 and R2 cis theta 2. The product is so simple. It is R1 R2 into cis theta 1 plus theta 2. When you are multiplying two complex numbers which are in the mod amplitude form, the product is so simple. The modulus of the product is the product of the moduli of the individual complex numbers. So, the modulus of the product Z1, Z2 is the product of the modulus of the first one and the modulus of the second one, which is R1 into R2. And what is the amplitude of the first one, theta 1? Amplitude of the second one, theta 2. You can see that the amplitude of the product Z1, Z2 is theta 1 plus theta 2. So, in the elaborate form, this is R1 into R2 into cos of theta 1 plus theta 2 plus I sin theta 1 plus theta 2. This is our Z1, Z2. And now you can see that what is Z1, Z2, Z2, Z3. So, Z1, Z2, Z3, the product of the three complex numbers is, it is a natural extension of this principle. So, it has to be equal to R1 into R2 into R3 into cos of, what should be the amplitude? The sum of the individual amplitudes, that is theta 1 plus theta 2 plus theta 3 plus I sin into theta 1 plus theta 2 plus theta 3. I sin of theta 1 plus theta 2 plus theta 3. This is our Z1, Z2, Z3. Okay. And one more important thing. If Z1 is R1 into cos theta 1 plus I sin theta 1. So, it is 1 by Z1. 1 by Z1, which is a reciprocal of the complex number Z1. If it is in the mod amplitude form, it is simply 1 by R1 into cos theta 1 plus I sin theta 1. Okay, this can be written as 1 by R1 into this 1 by cos theta 1 plus I sin theta is nothing but cos theta 1 minus I sin theta 1 in the numerator. Or you can write it as 1 by R1 into cis minus theta 1. Because we can write this cos theta 1 plus I sin theta 1 as cos minus theta 1 plus I sin minus theta 1. This can be written as this one. Because cosine is an eigenvalue function, you can replace cos theta 1 with cos of minus theta 1. And you can replace minus sin theta 1 with sin of minus theta 1. Because sin is an odd function. Okay. So, the reciprocal of a complex number, this one. All that you have to do is, like the modulus, which is a reciprocal of the modulus of the given complex number, and whose amplitude is negative of the amplitude of the original complex number. If the amplitude of the original complex number is theta 1, the amplitude of its reciprocal is minus theta 1. If the modulus of the original complex number is R1, the modulus of its reciprocal will be the reciprocal of this, which is 1 by R1. This is about the reciprocal of a complex number. Previously, you have seen what is the product of complex numbers. Now, what is the quotient of two complex numbers, which is Z1 by Z2. So, what is Z1 by Z2? The answer is pretty simple. This is R1 into cos theta 1 plus I sin theta 1 divided by R2 into cos theta 2 plus I sin theta 2, which is R1 by R2 into cis, this is cis theta 1 and this is cis minus theta 1. It is a reciprocal. Take it to the numerator and just automatically this becomes cos minus theta 1, minus theta 2. So it is cis theta 1 into cis minus theta 2. This is R1 by R2 into cis theta 1 minus theta 2. Cis theta 1 minus theta. So this is a quotient of two complex numbers. By the way, what is Z1 square? This is the extension of this is actually this De Moivre's theorem. What is Z1 square? Z1 square is Z1 into Z1. This is R1 into 6 theta 1 into R2 into 6 theta 2. This is Z1 and this is Z2. So naturally the product of these two numbers is R1 into R1. Oh, sorry. Z1 into Z1. Z1 is R1 into 6 theta 1. And again Z1 is R1 into 6 theta 1. Now the product of these two is R1 into R1, which is R1 square, into 6 theta 1 into 6 theta 2, which is nothing but 6 theta 1 plus theta 1. That's why Z1 square is R1 square into 6 2 theta 1. 6 2 theta 1. This is what we have here. Cos theta plus I sin theta whole square is equal to square for n equal to 2. Cos theta plus I sin theta whole square is equal to cos 2 theta plus I sin 2 theta. That is 6 2 theta. This is what we got here. Why this R1 square? That's a modulus. So De Moivre's theorem is a natural extension of this one just by excluding the modulus of the complex number. In this statement, we just exclude these moduli. We got the statement for this De Moivre's theorem. Okay, now, so I written the De Moivre's theorem statement once again. I am not going to prove it again. You can go for the previous video. You can go for the previous video to check what is the proof of the De Moivre's theorem. I am just going to repeat the statement for integers, for rational numbers. And then we proceed to find what are the nth roots of a complex number, particularly cube roots and fourth roots of a complex number 1. That's called unity. And again, a few problems. Right? So, this is the statement for De Moivre's theorem for integers. Cos theta plus I sin theta whole to the power of n is equal to cos n theta plus I sin theta for all n belongs to I. Now, for n equal to p by q. For n equal to p by q. That is n belongs to q. Q is the set of rational numbers. Q is the set of rational numbers. You know what are the natural numbers? Numbers of the form p by q, where p comma q are integers, and of course q is not equal to 0. Particularly, if q is equal to 1, this rational number automatically becomes an integer, and you can apply this theorem straight away. If q is not equal to 0 and if q is not equal to 1, if n equal to p by q, where p by q is not an integer, then cos theta plus I sin theta whole to the power of p by q is, I am repeating the statement once again, cos theta plus I sin theta whole to the power of p by q is one of the qth roots of cos p theta plus I sin p theta. One of the qth roots of this complex number cos p theta plus I sin p theta. It is pretty easy to understand. Think about this concept in simple terms. Look, cos theta plus I sin theta whole to the power of p by q. You can look at this way. Cos theta plus I sin theta whole to the power of p whole to the power of 1 by q. That is, now look, cos theta plus I sin theta whole to the power of p, where p is an integer of course. So, this is cos p theta plus I sine p theta whole to the power of 1 by q. So if this is z, this is of the form z to the power of 1 by q. You are going to find the qth roots of the complex number, this one, cos p theta plus I sin p theta. While finding the square roots, you are going to get 2 roots. While finding the fifth root, you are going to get 5 roots. While finding nth root, you are going to get n different roots. So while finding qth roots of this complex number, you are going to get q roots. Of these q roots, this number is one of them. There may be remaining q minus 1 roots. We will learn how to list out them in the subsequent discussions. Okay, so this is just one of the q roots of the complex number cos p theta plus I sin p theta. Say for example, if z is equal to cos pi by 6 plus I sin pi by 6, then what is z to the power of 3 by 8? What is z to the power of 3 by 8? My statement is z to the power of 3 by 8 is one of the 8th roots of z cube. Z to the power of 3 by 8 is one of the 8th roots of z cube, because you are going to write z to the power of 3 by 8 as z cube whole to the power of 1 by 8. That's why it is one of the 8th roots of z cube. Of course, what are the remaining 7 roots? We will learn how to list out the remaining 7 roots in the subsequent discussions. Okay. Right. So further, I have to define what are the nth roots of a complex number. Nth roots of a complex number, z. Right. Let z is a complex number. Let z is a complex number. A plus ib. You are asked to find what is z to the power of 1 by n. Nth roots of the complex number z. You are asked to find. Right. This is the power of a complex number z. We know that mod amplitude form allows us to write the powers of complex numbers in a simple manner, in an easy manner. So, for that you have to convert this complex number to the mod amplitude form. So, what is this mod amplitude form of the complex number j? Which is r into cos theta plus I sin theta, where r is equal to square root of a square plus b square, and theta is equal to tan inverse b by u. So it's pretty easy to find r and theta. So once you have r and theta, you have this z in the mod amplitude form. Now, this z to the power of 1 by n is r into cos theta plus I sin theta whole to the power of 1 by n. This is r to the power of 1 by n into this is cos theta plus I sin theta whole to the power of 1 by n. This is r to the power of 1 by n into, mind you, I have mentioned that cos theta plus I sin theta to the power of 1 by n is one of the nth roots of the complex number cos 1 theta plus I sin 1 theta. So it is one of the nth roots of the complex numbers cos theta plus I sin theta. What are the remaining roots? I am writing the remaining roots like this. So it is cos 2k pi plus theta divided by n plus I sine 2k pi plus theta divided by n, where k can take the values 0, 1, 2, 3, etc. up to n minus 1. 0, 1, 2, 3, etc. up to n minus 1. Maybe it's not visible to you on the board. So, I am writing somewhere. I am again writing this. Z to the power of 1 by n, that means r to the power of 1 by n into cos 2k pi plus theta by n plus I sine 2k pi plus theta by n, where this k can take the values 0, 1, 2, 3, etc. up to n minus 1. You are starting from 0, ending with n minus 1, and you are taking all the integers in between. So, we are going to get n different values for this k. For each and every different value of this k, you substitute it here, you are going to get a complex number, which is nth root of the complex number, z. For example, let's say one example for this. If z is say 1 plus sine, find z to the power of say 1 by 16. Find the 16th roots of the complex number 1 plus sine. Find all the 16 roots of the complex number z. How to find all the 16 roots? The process is pretty simple. First, you convert the complex number to its mode amplitude form. For that, first you have to find what r is, and then you have to find what theta is. So our r is square root of a square plus b square. A is 1, b is 1. So 1 square plus 1 square, which is root 2. And theta is tan inverse b by a. This is our b and this is our a. Our b is the quotient of a, which is 1, and a is 1. So tan inverse 1 by 1, which is tan inverse 1 by 1, is tan inverse 1, which is pi by 4. So our theta is pi by 4. Our r is root 2. Now our z is in the mode amplitude form. Our z is root 2 into cos pi by 4 plus I sine pi by 4. Look, you have just converted the given complex number to the mode amplitude form. That's what you have done in the first step. Now the second step is 4 z to the power of 1 by 16 is equal to 16th roots of the complex number z. They are root 2 into cos pi by 4 plus I sine pi by 4 whole to the power of 1 by 16. That is root 2 to the power of 1 by 16 into how to write the nth roots of the complex number? You got this formula here. R to the power of 1 by n, root 2 to the power of 1 by 16, because our n is 16 here, into cos 2k pi plus theta. What is our theta? Our theta here is pi by 4. So 2k pi plus theta, which is our pi by 4. Plus I sine 2k pi plus pi by 4 whole to the power of, divided by 60. Cos 2k pi plus theta by n, which is our 60, plus I sine 2k pi plus theta divided by n, which is 60, where K is. Where K is. Starting from 0. 0, 1, 2, 3, etc. up to n minus 1. What is our n? 16. N minus 1 is 15. So for each and every value of this K, you are going to get a different root complex. So for these 16 different values per K, you are going to get a 16 different roots for this complex number Z. So this single equation, Z to the power of 1 by 16 is equal to root 2 to the power of 1 by 16 into cos 2k pi plus pi by 4 by 16 plus I sin 2k pi plus pi by 4 by 16, where K takes so and so values. The single equation lists out all the 16th roots of the complex number from the side. Right. Let's look at the 16 roots individually, separately. So what are those 16 roots? So the first of them is, for K is equal to 0. So what happens to this? For K equal to 0, this becomes 0. So 2 into 0, which is 0, plus pi by 4 by 16. So it has to be root 2 to the power of 1 by 16. By the way, root 2 to the power of 1 by 16 can be written as 2 power half, whole to the power of 1 by 16. So it is 2 to the power of 1 by 32. Therefore, the 16th roots of the complex number Z, which is 1 plus I, are the first one, 2 to the power of 1 by 32. Because root 2 is 2 to the power of 1 by 2, whole to the power of 1 by 16, it is 2 to the power of 1 by 32 into 6. I am writing this complex number in the short form. Cos plus I sin is 6. So it is 6. Theta, what is theta here? For K equal to 0, this becomes 0. Pi by 4 by 16. It is pi by 64. That's the first root. So what is the next root? For K equal to 1, we will get the next root. So for that also, the modulus remains to be the same. So it is 2 to the power of 1 by 32 into 6. That is cos plus I sin. What is the amplitude? For K equal to 1. This is 2 into 1 into pi. So it is 2 pi plus pi by 4. So 4 into 2, that is 8 pi plus pi by 4. 8 pi plus pi. That is 9 pi by 4. 9 pi by 4 divided by 16, which is 9 pi by 64. 2 into 1 into pi plus pi by 4 whole divided by 16. This is the quantity here. For K equal to 1. This one. On simplification, 8 plus 1, 9 pi by 16. 9 pi by 4 whole divided by 16. It's the 9 pi by 64. Okay, what is the next root? For the next root, we have to substitute K equal to 2. So for K equal to 2, this becomes 2 times 2 into pi plus pi by 4 divided by 16. So this is 4 into 4, 16 plus 1, that is 17 pi by 4 into 16, 64. So 2 to the power of 1 by 32, the modulus remains to be the same. And 6, what is the amplitude? 17 pi by 64. There's the next root. So first root, second root, third root. What is the fourth one? That is 2 to the power of 1 by 32, 6. Now you can see the pattern. This is pi by 64. The next one is 9 pi by 64. So what is the difference between these two? The denominator remains to be the same. Pi and the numerator remains to be the same. It is 1 into pi. This is 9 into pi. So the difference is plus 8 pi. What is the difference between these two? 9 pi plus 8 pi, that is 17 pi by 64. For the next one, it is 17 pi plus 8 pi, which is 25 pi by 64. Will it be the same? Let us see. So this is for k equal to 3. This is for k equal to 0. This is for k equal to 1. This is for k equal to 2. And this will be for k equal to 3. So for k equal to 3, what will be this amplitude? 2 into 3 into 5 plus 5 by 4 all divided by 16. So this is 2 into 3, 6 into 4, 24 plus 1, 25. 5. 4 into 64 is 4 into 16 is 64. What will be the next root? 2 to the power of 1 by 32 into 6. What will be the next root? This is 25 pi by 64. So plus 8 pi in the numerator. 25 pi plus 8 pi. That is 33 pi by 64. Likewise, we can go for the, what will be the last one? The last one is 2 to the power of 1 by 32 into 6. What will be the amplitude of the last root? That is 2 into k. What will be the value of k for the last root? That is 15 pi plus 5 by 4 all divided by 16. So 2 into 15 is 30. 30 into 4 is 120. 120 plus 5 is 121 pi by 4 into 16, which is 64. So the last one is, says 121 pi by 64. Likewise, you can look at all the 16th roots of the complex number z into 2. If you are asked to write all the 16th roots, you have to list out all the 16th roots separately. You have to go for this. Otherwise, you can conclude the problem here itself. These are the 16th roots. We have all these 16 roots here itself. So we are mentioning different values of k for which we are going to get different roots. So once we have mentioned the values of k and give the structure of these nth roots or 16th roots, the problem is over here itself. If you are asked to identify the roots separately, you can go for this. That too, you need not evaluate all these quantities again and again and again. That's not required. Identify the first root for k equal to 0. Identify the second root for k equal to 1. Once you have these two, you can see that the modulus remains to be the same. Where the amplitudes, they will be in the arithmetic progression. Mind you, these numbers, they are in the arithmetic progression. Pi by 64, 9 pi by 64, 17 pi by 64, and 25 pi by 64, etc. All these, they are the numbers in the arithmetic progression. Look, all the denominators are exactly the same. 64, 64, 64. The numerator, this pi is common to each and every number. So, in effect, the sequence is 1, 9, 17, 25. The difference of 1 and 9 is 88. The difference of 17 and 9 is 8. The difference of 25 and 17 is 8. So what will be the next one? 25 plus 8, 32. What will be the next one? 33. 33 plus 8, 41. The next one is 49. Likewise, we can find all those. So it is enough to identify the first two rows. And then you can write the sequence just by adding the common difference for the amplitudes. Okay? This is a way to find the nth roots of any complex number. I have found the 16th roots of a complex number. For example, it is not 16th root. It is only the 5th root. What should be my answer? The answer is simple. Z is, we have already identified that modulus of this complex number is root 2. So root 2 into cos. We have identified the amplitude as pi by 4. So cos pi by 4 plus I sin pi by 4. Whole to the power of this z to the power of 1 by pi whole to the power of 1 by 5. This is 2 to the power of 1 by 2 whole to the power of 1 by 5 is 2 to the power of 1 by 10 into cos. Now I am writing the fifth roots. So the formula goes like this: 2k pi plus our theta, which is pi by 4, divided by, what is this 16 here? Our n. What is our n here? 5. Plus I sine 2k pi plus pi by 4 divided by 5. Where k is, for k can take the values 0, 1, 2, 3, our n is 5. So n minus 1 is 4. So the last value of this k should be 4. Starting from 0, you can see that 0, 1, 2, 3, 4, all the 5 roots. These are the 5 roots of the complex number z. Right. Now, let's find the cube roots of 1. What are the cube roots of 1? They are also called cube roots of unity. Cube roots of unity. So if z is 1, what are z to the power of 1 by 3? Still you have to reduce the complex number z to the mode amplitude form. So it is 1 into cos 0 plus I sine 0. Why? Because our r is square root of 1 square plus 0 square. Because of this 1 is 1 plus I into 0. So this is our 1. What is this theta? Tan inverse b by a or y by x. If it is s plus iy, y by x. If it is a plus ib, b by a. So tan inverse 0 by 1. That is our 0. So that's why it is r into cos theta, that is cos 0 plus I sin 0. Now z to the power of 1 by 3 is 1 into cos 0 plus I sin 0 to the power of 1 by 3. So this is 1 to the power of 1 by 3 into cos 2k pi plus theta. 2k pi plus theta. What is our theta? 0 divided by n. Our n is 3 plus I sine 2k pi plus 0 by 3. Where once I have introduced this k, I have to specify what this k is. K is 0, 1, 2. That's it. Because our n is 3, n minus 1 is 2. Okay. So, where are the 3 roots of this complex number z? 3 cube roots of this complex number. Suppose I want to look at these roots separately. So for k equal to 0, what is the first root? For k equal to 0, 1 to the power of 1 by 3 is 1 into cos. For k equal to 0, this is 0 plus 0 by 3, that is 0. Plus I sine 0. That's the first root. The next root is, again 1 to the power of 1 by 3, which is 1 into cos. For k equal to 1, this is 2 pi plus 0, that is 2 pi by 3. So cos 2 pi by 3 plus I sine 2 pi by 3. What is the last root? That is for k equal to 2. Again 1 to the power of 1 by 3, which is 1 into cos. K equal to 2 means 2 into 2, that is 4 pi by 3. Plus I sine 4 pi by 3. So what are the values? These are the cube roots of this complex number 1, cube roots of unity they are called. But I am not interested in this structure. I want to look at the numbers in the form a plus ib. For that, all that I have to do is substitute cos 2 pi by 3 and sin 2 pi by 3 here. And cos 4 pi by 3 and sin 5 pi by 3. That's it. So, what is the first number in there? general form, that is a plus I. Cos 0 is 1, sin 0 is 0, and this is 1. So 1 into cos 0 plus I sin 0 is 1. The next one is cos 2 pi by 3 and sin 2 pi by 3. So what is cos 2 pi by 3? And what is sin 2? 2 pi by 3 is minus 1 by 2. So it is minus 1 by 2 plus I into root 3 by 2. Or you can write it as minus 1 plus root 3I or I root 3 by 2. The next one is cos 4 pi by 3 plus I sin 4 pi by 3. Cos 4 by 3 is cos pi plus pi by 3, which is minus cos pi by 3, which is minus 1 by 3. Plus I into, what is sin 4 pi by 3? Sin pi plus pi by 3. Sin pi plus theta is minus sin theta. So it is minus sin pi by 3, which is minus root 3 by 2. That is minus 1 minus I root 3 by 2. So these three are the cube roots of the complex number 1. Right. If you call this one as omega, look, if you call this one as omega, this one will automatically become omega square. Is it? Let us check. Omega square is minus 1 plus I root 3 by 2 plus 1. That is, this is 4. Minus 1 plus I root 3 whole square is 1. Plus I square into 3, that is minus 3. Minus 2 times 1 into root 3 is 2 into y of course. A square plus b square minus 2ab. So this is 1 minus 3 is minus 2 root 3i by 4. Record this 2 as a common factor and cancel this one, you write it as minus 1 minus I root 3. So this is omega square. For example, if this is omega square. If this is omega square. That means square of this one is this one. Let us see. Minus 1 minus I root 3 by 2 square. This is a square, that is 1. B square minus 3. Because it is I square into 3. I square is minus 1. So minus 1 into 3 is minus 3. And minus 2ab or plus 2ab have both negative signs. So it automatically becomes plus 2 root 3 I. Divided by 2 square is 4. So it is 1 minus 3 is minus 2 plus 2 root 3 I by 4. Basics. Again take 2 as a common factor and cancel this the denominator, you will get it as minus 1 plus root 3i by 2. So 1 is the square of the other. 1 is the square of the other. This is a peculiar structure. Of the 3 cube roots of 1, one of them is 1, which is the real root of this equation z cube is equal to 1. The remaining 2 are complex numbers. These 2 complex numbers have a peculiar property. 1 is the square of the other. 1 is the square of the other. And if you can observe, 1 is the conjugate of the other. The conjugate of this one is this one. And the conjugate of this one is this one. You can see that the difference is only the sign of the imaginary parts. So this is omega. This is omega bar. So omega square is the other one. And the other root is the conjugate of the first root. So one is the conjugate of the other. That means omega bar is omega square. Omega bar, the conjugate of omega, which is this one, which is omega square. Okay. Now, there are certain important results regarding these cube roots of complex numbers. Cube roots of the complex number 1. Namely, 1, omega square. So what are those important properties? The first one is omega cube is equal to 1 because these roots, they are the, so in other words, you are solving the equation x cube minus 1 equal to 0. If you are comfortable with x, you can look at this equation as well. X cube minus 1 equal to 0. Solve this equation. That gives x cube is equal to 1 or x equal to 1 to the power of 1 by 3. That's why the values of x, which are cube roots of 1, these are the values of this x, which are solutions or roots of this equation. So, each of these roots should satisfy this equation x cube minus 1 equal to 0. So 1 cube minus 1 should be 0. That is pretty clear for you. Omega cube minus 1 equal to 0. That means omega cube is equal to 1. And omega square cube minus 1, which is omega to the power of 6 minus 1 equal to 0. That's pretty sure. Why omega to the power of 6 minus 1 equal to 0? Because omega to the power of 6 minus 1 can be written as omega cube square minus 1. And already we have observed that omega cube is equal to 1. So 1 square minus 1, which is clearly 0. So, in particular, omega to the power of 3k is equal to 1 for any k belongs to k is any integer. Omega to the power of a third multiple of any integer, omega to the power of 3 into k structure, it should always be equal to 1. That means omega to the power of 12 equal to 0. Since the power is a multiple of 3, omega to the power of any multiple of 3 should be equal to 1. Omega to the power of 12 is 1. Omega to the power of 24 is 1. Omega to the power of 33 is 1. Omega to the power of 123 is equal to 1. As long as the power of this omega is a multiple of 3, its value is 1. So this allows us to find all the integral powers of omega. All the integral powers of omega. Look, this is our basic omega, which is either minus 1 plus I root 3 by 2 or minus 1 minus I root 3 by 2. Either this one or this one. You can call either of this one as omega, of course. Now, omega square. If this is omega square. If this is omega square. So you know what is omega square. And then, what is omega cube? 1 by this result. Now, what is omega to the power of 4? It is simply omega cube into omega, which is 1 into omega, which is omega. So omega to the power of 4 is omega. Omega to the power of 5, which is omega cube into omega square, that is 1 into omega square, which is omega square. By the way, omega square can also be written as 1 by omega. Omega square can also be written as 1 by omega. How? That is pretty simple. Omega square can be written as 1 by omega, since 1 by omega is omega cube by omega. Because our 1 is omega cube. So omega cube by omega is written omega square. That's why omega square is 1 by omega. So you can write this omega to the power of 5 as omega square, or you can also write it as 1 by omega. And then omega to the power of 10, which is omega to the power of 9 into omega. Always search for the nearest multiple of 3 for this power. It is 10. The nearest multiple of 3 for this is 9. So omega to the power of 9 into the residue, whatever it is. That's omega. So this is 1 into omega, which is omega. So you can always find what is omega to the power of n, as long as this n is an integer. As long as this n is an integer. Omega to the power of 258 is how much? The answer should be one of these three. Omega to the power of 258 should be one of these three numbers. How? The answer is simple. Write it as omega to the power of. Look for the nearest multiple of 3 for this. Nearest multiple of 3 for this. Let's divide this number into 3. No problem. This is 8 times. 8 and 3, 24. The balance, 1, 18, 6 times. That's it. 86. Omega to the power of 86. Thank you. Or omega to the power of 86 into 3. This is our k. Omega to the power of 3k, as long as this number is an integer, the answer is 1. Or you can write it as omega cube to the power of 86, which is 1. Because omega cube is 1 and 1 to the power of 86 is 1. So, omega to the power of n can be just one of these three numbers. And one more important property for this cube roots of unity, that is 1 plus omega square is equal to 0. Sum of all the cube roots of unity should be equal to 0. Why? You have the three numbers here. Just you can add and you can see whether it is 0 or not. So this is 1 minus 1 plus I root 3 by 2. Sorry, plus the other one is omega square, which is minus 1 minus I root 3 by 2. This is 2 minus 1, and we have this minus 1 here, plus I root 3 minus I root 3. 0. 2 minus 2 is 0, plus I root 3 minus I root 3, complete 0 in the numerator, and this is 0. So sum of all the cube roots of unity is equal to 0. These are the problems. So I conclude here and I continue in the next class.